So what I want to go over now is light's behavior as a particle. So we've been talking about light and when it behaves like a wave. And if you remember, I said that Newton originally thought that light behaved as a particle, but scientists later showed that light behaved as a wave. Much later, around the early 1900s, scientists started figuring out light also behaves as a particle in certain situations. So I want to go over some of the evidence of light behaving as a particle and then what this means for us. So one thing that scientists observed, and which you probably have also observed, is that when objects heat up, for example, coals on a coal-fired grill, or if you think about like if you have some regular light bulbs, some old light bulbs in your house, what you might notice is that as coals heat up, or as the filament in the light bulb heats up, initially it will look kind of a reddish color. It will start turning orange as it gets hotter. It will start then turning yellow as it gets even more hot, and eventually it will look white. So what we see is that objects, as they're heating up, sometimes start emitting visible radiation, and the color of that visible radiation, the color of that light, will change with temperature. So scientists wondered, why does a wavelength depend on the temperature? If you remember from earth science, we see this with stars. The color of the star, the color we see with the star, does depend on the temperature of the star. So Max Planck, around 1903, he came up with the idea of black body radiation. Now, I don't expect you to fully understand this, but what I want you to understand from his theory is that energy that objects lose or gain is lost or gained in whole numbers. And the intensity, that means how bright, in this case, the light is, or the frequency or color of the light, does depend on the temperature. So he observed this, and then the question is, why is this occurring? So why does the wavelength change with temperature? What people started thinking was happening was that atoms in the objects can only absorb certain wavelengths of energy, and they will only emit certain wavelengths of energy. They can't just emit or absorb any wavelength of energy. It has to be certain wavelengths. And this would explain why objects, as they started heating up, will change color with temperature. So Planck came up with this equation. The equation is E, which is energy, times H, which is Planck's constant, times frequency, which we've been working with. So you notice Planck's constant is 6.63 times 10 to the negative 34th joules times seconds. And what he was saying is electrons can only have certain energies in the atoms. They cannot have energies in between. So let me just make this little electron move. So you think about electrons kind of move up in like steps. Just like when you're climbing a ladder, you cannot put your foot between the steps of the ladder. Same thing here. The electron could move from one step to another, but cannot exist between the steps of the ladder. It only has certain energies. So Einstein came along and said that this showed that light was behaving as a particle. And he called these particles of light photons. So he said that photons do not have any mass. They travel at the speed of light, but they have almost all the properties of particles with the exception of mass. And again, the higher the frequency or the shorter the wavelength, the higher the energy of those photons. So this is the first time we've heard the word photons. So this led to what we call wave-particle duality. That light behaves sometimes as a wave, sometimes as a particle. When light interacts with atoms, it behaves like a wave and like particles. In our world, usually light behaves like a wave, but when we get in the subatomic world, it's a little bit different. Now, another part of this, which we won't really get into, but your book gets into, is electrons in the atom also behave like particles and waves because electrons are such small particles. So very, very small, those subatomic particles also have behavior of particles and waves. Okay, so when we're talking about light as a wave, we're going to be using our wave equation. We'll think about the wavelength, the frequency. When we're talking about light as a particle, we'll call them photons, and we'll think of them as more of packets of energy. So the packets, photons, are more what we think of when we think of subatomic particles with atoms. Light as a wave is more what we think of on our scale of our world. It's another piece of evidence of this particle nature of light is something called the photoelectric effect. So I'm first going to show you this with this slide, and then I'm going to show you guys a simulation I found online, which will also demonstrate this. So what scientists also noticed is that if they had a metal plate and they shined like some red light or infrared radiation, some kind of low energy radiation on that plate all day long, nothing happened to that plate. No electrons were emitted. If they took that same metal plate, instead shined a very high energy light, for example, blue light or ultraviolet light on that plate, what is that the electrons started being emitted from that metal plate. This is called the photoelectric effect. And I'm going to, through the simulation, I'm going to show you more of what's happening here so you guys can understand the significance of this. Okay, so what I want to show you here is a simulation of the photoelectric effect. So in this simulation right now, we have a piece of sodium, and we're shining some low intensity red light onto this piece of sodium. As you can see right now, nothing is happening. So what I want to do is I want to change the wavelength of light that's hitting that piece of sodium. Let's go to yellow light. Let's go to green light. And you notice when I get to the color green that we start seeing electrons being emitted from that piece of sodium. If I make this light brighter, I'm going to notice a lot more electrons are being emitted from that piece of sodium. And if I increase the frequency to make it more energetic light, what I will also notice that electrons are being emitted faster from that piece of sodium. So there's a threshold frequency. If we're below that threshold frequency, so let's go back to the yellow light, nothing happens. Does not matter how bright that light is, nothing's going to happen. As soon as we reach that threshold frequency, we notice that electrons are being emitted from that piece of metal. Now let's change our sodium to, and let me turn off the light, go back to, we'll keep it the same wavelength, but let's change it from sodium to zinc. Now if I notice with my zinc, I can make that light very bright. I'm at the same wavelength that I was at for the sodium, but you notice nothing is happening. So let's increase the frequency. You notice here I have to go to a much shorter wavelength, a much higher frequency before I see electrons being emitted from my piece of zinc. Again, if I increase the frequency even more, I notice that the electrons are being emitted faster. If I decrease the intensity of the light, there's fewer electrons, but they're still being emitted faster. So let's go back down to our threshold frequency. I think it was about 262 or 259. Okay, so now let's change to different metal. Let's use copper. So we're going to keep the frequency the same. And you notice here, let's go to even lower wavelengths. Let's see. Okay, so copper has a different threshold frequency. And if we use platinum, let's change it to platinum. You notice nothing's happening. And it has a still shorter wavelength, a still higher frequency for its threshold frequency. So each element will have a different threshold frequency where it will start emitting electrons. If you're below that threshold frequency, no electrons will be emitted. So this is just the photoelectric effect, and it's another piece of evidence that light sometimes behaves like a particle. Okay, so what I want to do now is just summarize what you guys saw in the simulation about the photoelectric effect. And before we go forward, so the first thing that you saw in the simulation is that if light is at or above the threshold frequency and it strikes the metal surface, electrons are ejected. If light is at a higher intensity and is at or above the threshold frequency, then what we see is that more electrons are being ejected from the surface. Finally, if we increase the frequency, make it a higher energy light, that is, or higher frequency light that's hitting the metal surface, what we see is electrons are ejected faster. So these are the different things we observe with the photoelectric effect. And like I said, this is proof that light also behaves as a particle. Okay, so before we go over problems on using Planck's equation, I just want to reiterate this is Planck's equation, which I mentioned in an earlier slide. I just want to go over what the different parts of this equation are. E is energy, its units will be joules, which are abbreviated as J. H is Planck's constant, so will either use the value that's given to you on the homework, which is on Google Classroom, or you can use the value here. Nu is the frequency. Remember the units for that will be seconds to the -1 or 1/seconds or hertz. And then you'll notice here you can also write it in terms of wavelength and speed of light, and obviously lambda is a wavelength, and that unit has to be in meters. So this is the equation that you can use to help you to figure out the energy of a particular photon of light.